Hey, how it's going, guys? In this video, we're going to look at knowledge distillation. This is the only video you need to know about knowledge distillation, right? Let's say, you don't know about this technique, technology, substrate, whatever you call it, right? It's basically a model compression technique, right? And that's what we're going to look at because distillation is a key component when it comes to, training language models nowadays because of the way it works. You can basically distill larger models and get a very small model from that, right? And that's the agenda of this video. So it's a crash course. It's gonna be a little lengthy, right? I'm going to cover theoretical aspect, the definition, the types of knowledge distillation, the applications of KD or knowledge distillations, different models, a little bit of research papers, mathematical intuitions, and then we're gonna go into the code. So if you look at here on my screen, I have this, of course, my tab here. We're going to talk about it. And this is what we're going to train. You can see I just trained a model using distillation, using KD. You can see it's giving me a good response also, right? It says it's basically a question answering model that we train here. We distilled GPT-2, basically a smaller model running on free Colab. So that will be also very good because not everybody owns a high-end GPU like A100 or a V100 and whatnot, right? So let's jump in first theoretically and see what knowledge distillation is, why it's important, why there is so much of gaga about KD, right, in the AI ecosystem. Now, uh, one of the prime example of KD, that kind of got really highlighted is DeepSeek. DeepSeek based on distillation, and a lot of subsequent model from DeepSeek is also distilled from models like Llama, QNs, Mistrals, and so on and so forth, right? And this, what happens, guys, and I'll explain that DeepSeek was like they distilled from ChatGPT, Anthropic models, and so on and so forth. So they created a very is a lightweight model when you compare that with these big giants, and really in a very less it's by spending really less money and resources from a compute standpoint. And that's a frugal innovation, right? We call it. It's cool. And I want to just jump in and talk about KD here. So just for that sake, because I said, right, it's going to be a lengthy video, I'm going to cover a lot of things here. So it's basically a model compression technique. That's what it is. And guys, if somebody who does not want to follow along, this video is not for you. You should not spend your time wasting your time or spend your time on this video if you are not interested learning. And if you just want to kind of get into the code link will be available in video description through GitHub. You can just get it. So it's a model compression technique, right? That's what it is. The idea is very simple. There will be a the idea is like this, right? There will be a large model. So there will be a larger model or large model. We call it teacher model, and I will explain that terminology. And then we will have, let's say we have here a GPT-2 model or whatever, right? And then we will have a smaller model. So we have a smaller, like let's say a student model. So we have a smaller student model, right? And that's what happens, right? You transfer. We just transfer our knowledge, right, from a larger model, like let's say in this case GPT-2, to a smaller student model. And that's the fundamental behind knowledge distillation. It's a distilled, right? When we used to study in chemistry kind of a subject, right? We understand distillation processes. So that's how it works actually. And the reason is that people will ask you this question, right? What's the goal then? What's the goal here, right? So the goal is very simple. The goal is to kind of reduce compute, right? That's the goal, because not everybody owns kind of a high-end GPU. Then let's say if you want to train, see, you can train models on H100 and A100 GPUs and tons of GPUs, like a lot of bigger players like OpenAI and Meta, they do it, right? But people sitting in a small apartment can also train model, guys. Trust me, that's how we have been seeing recently, and that's all frugal innovation, right? In India, we call it jugaad, right? It's a jugaad kind of a thing, right? So that's important. So reduce compute, compute, we reduce memory here, we reduce latency. So that's the fundamental, right? And the good thing about KD is that we want to keep the accuracy level as much as high as possible. So keeping most of the accuracy. Of course, there will be trade-offs, and we will see that. But yeah, that's the fundamental actually. So analogy is very simple. Like let's say there is a PhD student, not a student. Let's say a PhD professor, a teacher, right, who kinds of write simplified notes, and that notes can be consumed, by a high schooler, right, a high school student to learn faster without reading the entire book. That's the simple analogy that we see, right, behind it. Now we're going to talk about it a little bit on the applications, and then we'll go into the mathematics and the other thing here, how it works. Now the application, if I write it. Okay, let me just write about the applications here, guys. So let me just do that. So the first application is to deploy a smaller model because the world is moving toward SLM, right? One of my idol, right, that I really admire, Andres Karpathy, he was saying that agentic AI evolution will be, of course, empowered by small language models, right? Because SLMs will play a huge role in the agentic AI adoption across industries, right? Mainly in the IT industry, the enterprises, the small models, SLMs will play a huge role. So deploy small models. I wrote here. I don't know why why I wrote here this one word actually. It has to be small models. So that will be like SLMs. So we're gonna look into the SLMs here, right? Deploy small models, inference speed up. So like let's say you want to inference, speed up the inference, right? Our post training, we have to look at the inference part. So I'm gonna write inference speed up. That's the next thing that we look. Now, in a lot of the regulated industry, right, we have privacy preserving, where we want to kind of run everything on edge devices or on devices, right? So privacy preserving AI, that's called PPAI, right? So I'm writing PPAI, on device AI basically. So that is a fundamental application, with all these frugal innovation or the things that we call it. Now, the good thing is domain specialization that has a direct kind of a connection with smaller models, because smaller models are good on specific domains. Like let's say you want to train something in healthcare, you want to train something in insurance, you want to train something in agriculture, you want to train something in manufacturing, so on and so forth, right? So the smaller models kind of understand specific domains, and that's what one of the applications of knowledge distillation or AI distillation or whatever you call it. So I'm going to write it here called domain specialization, that is based on speciality. So I'm just writing here, specializations and something like that. Yeah, domain specializations and ensemble compression. That is a very good research area, guys. And I'm just writing here. I'm not going to talk a lot about this because there are a lot of compression techniques, right? Instead of running, let's say, large models, like let's say 10 large models, we can distill them into compact student, right? Distill them into one compact student kind of a thing. So that's ensemble. This is a good research area. And if you want to research about it, do research on this as well. Now, the next thing is how many types of KD we know, right? That's the thing. So there are different types of distillation. So I'm gonna write that here. Let's write types of distillation. So I'll look at types of distillation here. Now, there are different types of distillation, of course, and when it comes to kind of explanation, when we're writing the code, we'll see which one we are kind of going to look at. The most famous one is response or logit distillation. So I'm just writing here logit. So I'm just writing logit distillation. So that's the logic distillation. Basically, students learns to mimic, a teacher's softmax kind of the probability output. So whenever logits are there, you would have studied the softmax functions like logistic regressions and so on and so forth. That's what logic distillation comes up. The student learns to mimic that. Okay, they learn of course it's a, if you look at that, right, it's a pattern only. So it learns to mimic the teacher's softmax probability outputs. That's what it is. I'm writing here in a kind of writing here. So let me just write it like this. Student learns to mimic teacher's softmax probability output. probability outputs, and this is the most famous one. That's why I like kind of I've written it over here. Otherwise, I'll just write it like this. Then there are feature distillation. So we have feature distillation. Concept is very simple for feature distillation. It just learns the intermediate hidden states, of the teacher. So that is the one. Then next we have here attention distillation, and this got more famous because see, distillation is not a small, it's not a very new or a latest kind of a technique. It's an old technique, but the attention distillation came in picture when the transformer was like on the rise, because a student mimics the teacher's attentions map. It's self-explanatory, and that is of course when you learn transformers you will understand that. I have a video on that, please watch it, where I have trained how to train LLMs from scratch in pure Python, PyTorch, no framework. So you should look at that as well. And in distillation, then we have self distillation. Now, self-distillation is also a very important topic, because in self-distillation, a model is its own teacher, by the way. So, like it's fine-tuned on its own labels, over iteration. So that's a very interesting concept. You should also look at this, like, I just make it a circular thing here, because you should read about self-distillation. Very interesting concept. So that is the one thing. And the last one can be a task or a domain. So let's say I write here task or domain distillation. So that's what is this. It's basically a transfer knowledge kind of a thing, of general LLM into a student focused on one task. Like let's say biomedical question answering and agriculture question answering. So I have done something on task and domain distillation, where I kind of, when I was working in a startup where I did that. I'll show you here when I write, like let's say, and I'm gonna show you that here. This is on that where we use distillation to kind of, you see this, right? This, you can find my name here. All right, you can see democratizing cost-effective agentic AI to multilingual medical summarization. So here the thing is, it's a combination of distillation KDs here. So we will kind of use logit plus task or domain distillation. So on the task or domain, if you see for this paper here, it's medical summarization. So we use summarization techniques, to kind of sorry, KD techniques for medical summarization. That's what we did here, right? So if I show you, I'll just make this that's fine actually. I'll just make this a little bigger so you can read that. Yeah, you can see it over here. We kind of compare that because the data was in Arabic. So we compare that with one of the Arabic's based model called JAS. So you can see it was compared with JAS here. We did really good actually. Looking at this, we performed really well given the data that we had, because you can see the pairwise comparisons of 400 samples on the validations, and you can find out we performed really well. So this was based on distillations actually. Amazing, right? You can read about this, go and read that. You can find out the data availability. Amazing, guys. This is fantastic. All right. Okay. Now, coming back to this, one second. Let me go back here. All right. Let me go back here in our thingy. Now, we talked about these things. Now, we're going to look at this. There are some key algorithms of KD. Okay. So you should learn about that if you want. And I'll write that here. So the key algorithms, if I talk about it, what are some of the key algos, of this topic? Fundamentally, there are three, four, the research paper that you should read. One is soft label matching. So soft label matching is the one. So soft label, matching is by Hinton, by the way. So you should read that paper. So let me just show you here. I was reading that paper actually. Soft label matching. If you write Hinton, you'll find that paper. Right, improve, you can see that improve knowledge distillation. Not this one, my bad. I'll give that link in the description of this video. I have to find out, it's in my another laptop actually, but yeah, that's the one. But you can find out, yeah, this one from Hinton's perspective. Yeah, well, here you can find out. So it shows the evolution of this one. Yeah, you see it here. The concept of knowledge distillation emerged in 2015 with Jeff Hinton. This paper, Distilling the Knowledge in a Neural Network. Yeah, this one. My bad. Yeah, so you should read this. Excuse me. It's based on soft matching, soft label matching, by the way. The paper name is not soft. Yes, this one. Yeah, this is the one. I remember the word soft level matching, so I was like looking at it. Yeah, you can find out everything about this. Is a very good paper if you want to understand that. I'm not covering that paper here. It's just to minimize the KL divergence, and we'll talk about those things. It basically minimize KL divergence, between the teacher and the student's output, and that's the that's how we should look at as the loss function for KDs, where your ultimate target is to minimize the KL divergence. So let me just write it over here so you can see it. Let me go back now. I'll just close this for now. So the idea is to minimize the KL divergence. That's the idea. So let me just write it here. Minimize the KL divergence. Now I'll just go back. And then there's PKD. There's PKD, patient, I think it's patient knowledge distillation. Yeah, patient knowledge distillation that basically distills the immediate layers, not only the logits. So this is a very good algorithm that you should look. There are other models which were kind of influenced. They're like special architectures. One of the famous language model that we have seen is TinyBERT or MobileBERT, whatever you call it, right? They are based on architectures related to KDs. From BERT, they are from BERT-based large model that we have seen. So they are distilled from such models. DistilBERT, DistilBERT is also there. So you should look at DistilBERT. Hugely popular. It's 40% or 50% smaller than other, or the BERT performances that we have. The main one, the large one, 40% smaller, and really faster. I think it's 2x faster than such models. And then we have other models like MiniLM, etc. So these are some of the models that we already have. Now, mathematical intuition is a bit. Let me just come this side a little bit. Yeah. Now, yeah, the thing is, we'll look at the mathematical intuition here, a little bit of mathematics here. Now, I'm not going really in detail, like, but let's say the loss function. I'll only talk about the loss function here, and then we'll write about. I've written the formula because I haven't memorized it, but it's very simple, right? You will have teacher's output, you will have your student output, and then you will have a temperature value. That basically temperature is used for something called dark knowledge. In this field, I will talk about it. It's not like how we, of course, very similar to how we say creativity or randomness when it comes to LLMs, but here it softens the logits value. So it has, if it's greater than, like, let's say 1, it softens the logits. So temperature is for dark knowledge. So dark knowledge is a term. So let me just write the match here once, and then we'll talk about, or we'll explain that. So here the formula is like that. So we'll have, and let me see. Of course, I don't remember this formula actually. And I hope that's the right formula. I got it from the paper itself, and we'll just talk about it. You see this T square value, we're going to talk about is temperature square. Okay, and this is basically is the KL divergence between now I'm gonna, whatever I'm writing now, the next is the KL divergence equation, and this is the most important. So it's called KL, and then basically, of course, we'll have. Let me see that. Yes, T. Of course, it's again a probability value. PT. Yeah, it's PT. Is correct. Now, fantastic. So this is the formula of distillation that you see. Now, this value that you see, now I can explain this better. This value that you see, this is nothing but your cross entropy loss between student and teacher, student and true labels, whatever true labels are there, and the student labels. So whatever output basically it generates, right? So this is the cross entropy loss. We know that. And guys, don't do vibe coding and all for this. This will not work out. You need fundamental understanding. So a cross entropy loss between student and true label. So that is the ultimate thing. This value that you see is very important. This is what the KL divergence between teacher and student is. Between student and and student and teacher distributions. That's what it is. At temperature T. So if you see that T, it's it's pretty much straightforward. When you have QT or PT at temperature T value, right? And this these two things that you see, if you this is pretty standard. They are all nothing but they are coefficients, right? They are balancing coefficient. So I'm just writing it here. They are your this is wrong. Spelling is wrong, but you can find out. This is balancing coefficient. So this is the formula. Right? Intuition is very clear. This first part that that we have ensures that student doesn't forget the real labels. This part that you see in this equation, this part that you see in the equation, this is the intuition is pretty simple behind it, that this student does not forget, right? So the thing is, student does not forget the real labels. This is the fundamental thing. The second part is for the dark knowledge that I was saying, right? It's nothing but probabilities over non-correct classes. It's the dark knowledge, right? When probabilities over non-correct, which is not correct, okay, classes from teacher to student. So this is basically transfer, okay, of the dark knowledge. So this is how the intuition is behind this mathematical formula that you see for knowledge distillation, and we're going to talk about it. So two things that you have to keep in mind, if I just summarize it in a nutshell before we go into the coding part. Okay, so and of course we're going to look at that. Keep in mind student, teacher, KL divergence we talked about. Yeah, these three things you should know, right, before going into the code, which is important. So I'm going to use free collab, and of course this will be available to you guys. I'll give probably this also, if you want to go through it later. Want to cover that little bit of theory before jumping into the practical or directly showing the code, because distillation is one of my favorite topic. I do a lot of research in this area, by the way. So yeah, and I don't memorize the formulas. Okay, so let's come back, okay, at our coding thing here. So if you look at this, I have my AI distillation. I'm not going to write cell by cell. I will explain you, pretty much straightforward thing. So what we are doing here, right, we need bits and bytes. You can see, let me just reconnect here once. Now let me just reconnect quickly here. Okay, so you can see we are using bits and bytes here for, of course, for bits and bytes, why we use it for LoRA configs, for all kind of compression thingy, quantile quantization, QQ, right? All these things are based of it. So we're gonna use a wiki text data set for this experimentation. Later you should basically change the data set to any instruction data sets like alpaca, for example. But yeah, you can see we have bits and bytes, and now I have all of my dependencies that I have been you know uh, I have kind of imported here. You can see we have torch, we have data sets to work with Hugging Face data sets. We have transformers. We're getting auto model for causal LLM. We have auto tokenizer. We have bits and bytes config. We have trainer and training arguments. So let's just get in here quickly. I hope that is installed, right? Otherwise, we have to install that. Yeah, we have to install because the connection runtime was kind of, it was disconnected. So I had to install it again. All right, we'll go through it. Okay, this is done. So let's just run this now. Now, if you look at the next one, what we are doing pretty much straightforward. So we are checking if there is CUDA available on this environment, whatever compute we have. So it checks device equal CUDA, and if torch CUDA is available, as CPU, and you can see that we are looking at BF16. It's a kind of a data type. It's kind of a data type, yes, for the tensors. So you have F16 and BF16. So BF16 is supported on Ampere architectures like A100 and etc. If you're not on A100, it will automatically be using F16, right? So that's what we are looking here. So if you run this, it will show you that if the device is CUDA and what is the CC measure and so on and so forth, right? So that's what it is. And if we just talk about a little bit of custom KD loss, I forgot to write that. I will just write it here. Pretty much straightforward. Okay. So this cross entropy, that how this formula can be narrowed down for if you want to memorize that. I was like on the lighter note I was saying. So let's say if you want to memorize the formula, I think the best way to memorize is, let's say we have an alpha and then we have the cross entropy loss. So alpha multiplied, of course, cross entropy loss, and then we have beta, and then we have our temperature value, so T2, which is and KL divergence. So this is the formula. You should remember it pretty much. This is the formula. This is like a custom loss. So let's me write it as a custom loss. So we're going to use this custom loss formula. We're going to code this and look at this loss function when we are coding it. So that's what the idea is, right? And I hope you got it. So let's just go back here. Now, the next thing that we're going to do is we have some configs, right? So the notebook that I have created is pretty much modular. So let's say you already want to use this on A100 GPU, it will automatically, you just have to do free equals to false. The moment you do free equals to false, it will use all the higher end GPU configs. So on free collab, I cannot use these larger models like Mistral or Tiny Llama. But if say you want to try it out to train a very good model, everything will mostly it will remain same. You just have to change a little bit of tweak. So you can see here I'm using teacher model as GPT-2 and my student model is distill GPT-2. I have load in 4-bit false, my block size, my training tokens, val tokens, because I have to be careful about my compute. So this is what I have, right? Now the next thing is my learning rates and my other config, the temperature of KD, which is extremely important, guys, to understand the temperature value. As I said, right, temperature softens the teachers and students logits, and that's very important to get that. So CE is nothing but cross entropy is basically that mix with, if you look at the CE weight, and I will talk about it, why we have 0.2 or 0.8 as an alpha and beta value for balancing, as you know, right? And output directory is KD output. So let me just run this for now. Now this is pretty much straightforward. NF4, right? It's a quantization type called NF4 for bits and bytes. We are loading in, if loading 4-bit, which is not true, we are loading in 8-bit anyway. So I'll just run this. Okay. And you would have probably figured it out on LoRa and when you have been working with fine tuning. I have a lot of videos on that, guys. Go and watch that videos actually. Now here we have a teacher tokenizer that you see, right? In this teacher tokenizer, now we have our teacher model that we are loading. We are using padding, making sure the pad token is correctly initialized right over here. So this is used to get the teacher, and we froze some of the layers. So you can see we are getting the teacher model. We are just okay. Let me just run that also. Otherwise, I'll forget. I hope I have run this. No, I didn't run it actually. My bad. Which one did okay, well, that's fine, I think. Yeah, because this has ran, right, or not? Yeah, seems like that. Yeah, you can see. And now here we have our student model, the same thing. So let me just run the student model here. So let me just get it. Now it's important for you to understand. We might ask this question: why do we have here, like, let's say teacher value as 2? Higher T reveals more dark knowledge. That's the fundamental. Dark knowledge, start with T equals to 2. That gives you a balance. Now, if you have noisy labels, like let's say in your data samples, if you have noisy labels, right, or pure LM and no labels, right? So then this alpha values would be 0 to 0.2, and then beta value from 0.8 to 0.10. It's like for supervised task, if you want to if you have a supervised task, you can raise the alpha value. That's how it is. And of course, we'll talk about these things, LoRa things later. So let me just go down here. This is fine. So here what we're going to do, right? Let's see. So we are using LoRa config, low rank adapter, right? Adaptations. So LoRa config and get PEFT model. Now in the LoRa config, and I'm not going detail into LoRa, I have a fine tuning video crash course of around, I think, 90 minutes. Watch that video. I'll give the link in description. That's a very good video actually. Now, if you look at here, right, we are identifying the target modules, and not all target modules will have QKV, right? GPT-2 does not support that QKV projection. It supports C attention, CFC, and CPROS. So I have different, and this is fine because if you are using llamas or Mistral, automatically it will take this, and if it not, then it will take this one. So I hope you get that point actually. Now I'll just run this. And you can see the target head and a LM head that LoRa targets, LM head, and fan in, fan out false. So we're gonna now this LoRa config is interesting. Like guys, it's very interesting. Like why do we select R equals to 8, right? It's a sweet spot. People keep it from 4 to 16. You can keep it the rank, and 8 is the sweet spot, and that's why people keep it basically, right? So that's the fundamental thing. So I'm just gonna run that here. So let's just run it. And when you run that get PEFT model students LoRa config, it will show you the trainable parameters. So you can find out this is the trainable parameters. Like we can train around 0.49, like 49%, if I'll say, trainable parameters from that particular model that we have. And here what we're doing, we are building our data sets here. So let me just run this. I'll just skip this part for now. Like these are all data sets. You can go Wikitext to find out these on Hugging Face. These are all from Hugging Face actually, right? So you can look at that. We are creating training sets and validation data sets. Data quality should be, like data quality greater than size for fast demo guys, like 50K to 200K good tokens already show gains. Like that's my agenda of this video, to show you that it works, right? KD works, knowledge distillation really works, and there are different ways we can do knowledge distillations. Okay, uh, so yeah, let me just find, if you want to increase that, you can increase it. You can see we have a very small training sample of 782 and validation sample of 79. That is fine. So let me just go up, right? I'll just run this collab function. I have explained each of these guys in my previous videos, so please watch that videos, right? KD loss, and you can see this is where we are calculating our loss thingy. So as I told you about this formula, so if you see alpha dot cross entropy loss plus beta into, of course, T square temperature square for the dark knowledge transfer into KL divergence. So we want to minimize the KL divergence between the student and teacher logits. So what we are doing here, you can see we have KD loss. We are passing the student logits, teacher logits as params, labels T2, which is our, of course, default alpha, the value that we set. And here we calculate the cross entropy over here. You can see this is how we are calculating it. We are using the cross entropy module that you see here. It's a cross entropy module that is available for us to use it. And then we just use that. And after that, we are getting all the logits through softmax function that you see, log softmax. And then we just calculate the KL over here. So if you look at the KL divergence, we are getting f dot KL div. And of course, passing the student teacher reduction batch mean, and then T square that I talked about it, and returning the alpha into C plus. Pretty straightforward, right? Nothing. But by the way, KL has been multiplied here with T square, so don't get confused. So if you look at this formula, right, this is the formula we have here, right? So this is the custom loss function, but this is not the ultimate thing. If you want to change this loss function, you want to improve it, you can also do that. It's up to you, right? Read more research paper and find out how to improve KD workflows, right? Or KD architectures to kind of create better models. Now, here we have class KD trainer. In the newer Hugging Face versions, there is a number items in batch available. So I'll just run this here. Okay, compute loss. This is pretty Hugging Face thingy. If you train any models, you will do the same things almost. Now here we have a training arguments. We are passing the output directory. We are giving the train batch, eval batch, and accumulation steps. We have a learning rate, our number of training epochs, logging steps, eval strategy. Don't call it evaluation strategy. In the new Hugging Face, like the libraries that we have, it has been updated. That's why I've written it over here. And you can see we have 16 and everything, that is fine. And now here I'm running that trainer, KD trainer, and passing it. And I want to run it on like 50 epochs. You can train for more epochs if you have a very good data sets. It all depends on data sets, guys. So let me just run that here quickly. I'll just run it. So it's going to take a little bit of time. And it's fast. It's not really like some big data set, so don't worry about it. Okay, so that's actually fine. We can also push it to Hugging Face. I'll probably push it later because that's a small model, not that good actually. And if you look at this, it gives you global step, training loss, metrics, train samples, etc. But I'm not a huge fan of these losses. We need to calculate perplexity score here. So perplexity is a good measure, not that perplexity startup that for like that does web search. it'll find out for the eval step. So you can see we get our perplexity score over here. It says eval lost this perplexity, not a good model, not a good model if you look at that way. Okay, but that is fine for this particular video, because I wanted to introduce KD. I want to show you that how we can use it. Now, if you look at this, right, it basically creates all these files that you have, right, because that files will help you push that to your Hugging Face, right, and use it. Now, I'll show you. Let's try it out here. Earlier, it worked in the last one. Okay, so you can see we have a prompt here in healthcare AI. We're going to give the inputs, student eval, and you can find out for your student pipeline here, the model, student model that we have. Now with this one, we are just generating a new tokens, like let's say 120. I want to see how the model kind of gives. If you look at here, it gives you this output. It says in healthcare AI, knowledge distillation helps small models by allowing them to perform a variety of tasks. Fantastic, because in the prompt, we have only till this small models. After that, it's generating here. You can see small models by allowing them to perform a variety of tasks. The researchers used their data on nearly 4 million patients in first 10 years of clinical trials. 6.5. This is fantastic, guys, right? So it's able to generate, right? Now the idea here is to kind of perform this on specific task. Right now, this is question answering. You should do it for summarization. You should do it for entity extractions, and you should do it for such things. So that will basically help you, even master this better. So this is what I wanted to. So now you can also push it to Hugging Face Hub. Just use the HF API to push it, and you can just use push to hub also to push it. So not a big thing. If you want to push it or not, you can do it. Keep it locally, because these models are not that big in size. Like you can just get it in something. But yeah, that's what it is. You can see how we did GPT to distill GPT-2, right? Teacher in 8-bit and students and LoRA. We combined that actually. This is fantastic, right? I'll give this notebook so you can try it out and learn about this thing, guys, because you should train your own models. That's the idea, right? Of creating, and you don't always have to rely on those heavy computes and whatnot, right? You can do it on limited compute also. So I'll give this notebook, check it out. Let me know what are you training with this model, what kind of data sets you are using to do that. Probably I'll also give you this, if you want that actually, on knowledge distillation. And go and read this research paper of DeepSeek and the Jeff Hinton paper, which is really cool actually. This one, distilling the knowledge in a neural network. Fantastic, right? That's all for this video, guys. Before I wrap up this video, I want to show you an agentic AI toolkit that I have created for you. Okay, that contains 150 plus N8N workflows. It contains a 3 months of learning roadmap for people who wants to learn AI agent. And it contains a few frameworks and methodologies and templates for you to build agentic AI like a professional. So get that. You only have to pay once, and you get lifetime updates. Every week, I am pushing around 50 N8N workflows. Those are complex workflows. Those are tested workflows. So you'll get that workflows. I'll give the link in description. Check it out. Right. That's all for this video, guys. Please hit the like icon if you like the video. If you haven't subscribed the video yet, please subscribe. If you haven't subscribed the channel yet, please subscribe the channel. And I hope you learned about knowledge distillation in this video. And please share this video and channel with your friends and to peer. Thank you so much for watching. See you in the next one.